All right, here we go. Resistance in electrical systems. Take your notes, take the quiz afterwards. Let's get through this together. All right, introduction here. Resistance when charge flows through a wire. Why is that? Because electrons flowing through a wire, you're always going to have some kind of resistance. We always try to minimize that resistance by using different materials, but that's something we'll talk about in a minute. The amount of resistance depends on the size of the wire and its material composition. So smaller wires or bigger wires, what's going to matter? What changes between those two different things? Usually we have bigger wires to carry more electricity and smaller wires to carry less electricity. Okay, conductors, insulators, and semiconductors. What kind of conductors are we talking about? Well, that is a conductor, but not the right conductor. The kind of conductors we're talking about, that's going to be like copper wires. You can look at, not fiberglass, fiber optic cables, other things like that, things that carry are the internet signals, things that carry power signals, telephone signals. All those things are different kinds of conductors. Talk about insulators here in a minute, and then semiconductors. All substances can be rated by their ability to conduct electrical current. Some are very low electric current conduction, and some are very high conduction. You use very high conductors to actually make things move electricity. Things like copper are good at that. Steel, aluminum, those have different values of conductivity, but they are still conductors. If you have wood, it's not a very good conductor, and it even falls into the insulator category. Materials, some liquids and plasmas are good conductors because they contain many free electrons. So the more free electrons you have, as in liquids and plasmas, and then metals and other materials have lots of free electrons. So electricity can move, because electricity is the flow of electrons from one place to the other, flow of electrons. In a conductor, electrons flow easily, but there's always some resistance that inhibits the flow. Like I said, we try to minimize that resistance through our power usage and through telephone lines and internet resistors, or internet signal travel. We try to minimize that amount of resistance to increase the distance of that electrical flow can be and reduce the cost of it. All right, so materials that resistance disappears at very low temperature, they're called superconductors. So what kind of things would be superconductors? Typically, those are things we're trying to put into our microchips and things like that to cause superconduction because there is very low resistance. Most non-metal solids like wood and rubber are insulators. So rubber ducks, definitely insulators. Not the best example of insulators, but they're definitely an insulator because they're made of rubber, which is very resistant to the flow of electrons. So if you think about it, if you're in a car or wearing rubber boots and some kind of electrical shock happens, then it's better for you because you have some kind of resistor on there to where it's hard for that electricity to ground out because there's a resistor there. In insulators, electrons are tightly bound or bonded, so insulators conduct very small currents even when large potential differences are applied. Some substances, such as silicon, are intermediate in their ability to conduct charge, and they're called semiconductors. So semiconductors is also something we use, if you've heard of silicon, that's something we use in microchips as well because it conducts and is pretty middle in their ability to conduct charge while still being a resistor, but not too resistant, but they also still have charge and flow. All right. And the important thing about silicon is that it's a very soft or almost brittle metal. Even though it's still falling into that metal, non-metal category, it's actually something that's very easy to form and shape into microchips specifically. So electrical resistance. See our ohm meter here, it's a big example of this. It's something that measures electrical resistance. So it's an ohm meter, or you can say a voltmeter, depending on how many functions it has. This one looks more like a voltmeter too. So electrons do not flow in straight lines in a wire, but they bounce off the atoms in the wire. So if you think about electrons, they're very free moving. They want to move around, up, down, left, right, backwards, forwards, up, everywhere they want to go. They barely, in this case, they're probably not going to go backwards, but they're going to try and bounce around all over the place on that wire. And that's what causes the resistance because it's touching the walls and causing those electrons to start to lose energy. Electrical resistance is defined as the ratio of potential difference or voltage drop across the device and the resulting current that flows through the device, or resistance is equal to the drop in change in voltage divided by the current. Wow, dropped there for a second. The unit of electrical resistance is the ohm. That's why that thing is called an ohm meter, because it measures ohms. So the big deal thing here we're looking at is resistance voltage drop. So that's the difference from the beginning of where the electrical source is to the end where it's trying to get. Ohm's Law. So we're looking at ohms, and it's talking about states of potential difference is equal to the product of electrical current and resistance in a circuit, or change in voltage is equal to current times resistance. Big equation here. VIR. V is equal to IR. So I put in this plug here because it's the best example of a circuit that you probably use every day. When you plug in that electrical outlet, you're actually closing the circuit and causing it to actually let electrons flow. If it's just a plug sitting there, there's an open circuit. There's not actually connected to anything. So once you connect it, now it becomes a closed circuit and electrons can now flow. So it's constant for most conductors. So that ratio of potential difference to current is constant for most conductors. That's why we can use this equation. Okay, so here is your first quiz. Take the time, pause the video, and answer it. I gave you an example of a series circuit. We're gonna use the VIR equation. So voltage drop is equal to current times resistance. Good luck. Here's the answer. You have your givens with the unknown, you have your equation, your substitution, and your solution with unit. That's why we want to try and do it every time. It's a good thing to practice to do it now as well. So change in voltage is equal to current times resistance, 7 times 15 from our questions in the problem, and it's equal to 105 volts, because 7 times 15 is 105. Hopefully you got that right. Let's move on. So part 2 here, resistivity. So big word for resistance, different way of saying it. So what is resistance? This is now the measurement of that. We use the Greek letter rho is a measure of the capacity of a material to resist electric charge flow, measured in ohm meters. So it's a measurement now. So you see I got some pictures of resistors down there. It's different things that happen, different ways of doing that help with circuits. The length of the wire. So that means the longer the wire, the greater the resistance. So you have a really long run of wire, greater resistance. Radius or cross-sectional area of the wire, the smaller the wire, which means the smaller the wire, the greater the resistance. So if you have a really small pipe versus a big pipe in the same sense, it works the same idea in wires. Small wires have greater resistance because they're bouncing, the electrons are going to bounce off those sides of that wire more than if you have a really big wire, because it has less resistance, because it has more chance to move without actually hitting the walls. The material of which the wire is composed. The higher the resistivity of the material, the greater the resistance. Pretty self-explanatory there. Resistance in a wire is the resistivity, rho, times length, capital L, divided by the cross-sectional area, or A. So what is cross-sectional area? So that's if I took this can here, my little Pepsi can here, and if I took that and chopped it in half like this, that would be a cross section, because you'll be able to see through the cross or the middle of this can. Take a cross section of that. So if I take a wire, cut it in half, I got a flat wire here too. If I take this wire, a little flat wire, cut it in half, I would now have I could take a cross-sectional area of this. It's a lot easier with a flat wire because it's flat versus a round wire. You have to cut that thing in half. Series circuit. So what's a series circuit? Goes around in a series, right? Keeps going around in a series. Just think about what's the World Series? 7 games. 1, 2, 3, 4, 5, 6, 7. They go around in that series. Current has only one path and remains the same everywhere in the circuit. So there's no change in the current, and it's going to be all the way around in one motion. In my little example here, we have a battery and 3 light bulbs. You see that it goes from wire to wire and always goes in the same direction. Doesn't change, isn't able to go any other way. It's one path. Total resistance of a series circuit is the sum of the resistors and devices along the path of the circuit. So you just add them all up. R1 plus R2 plus R3 plus R4, all that stuff just adds up to each other. The sum of the voltage drops across the device equals the total potential difference of the power supply. So potential difference around this would be, our power supply would be the battery in this case. Total potential difference also equals the product of the total circuit resistance and the current. So that's VIR again, still using that same thing. We're just adding in some more R's. We just add the R's up to get that big R. When a switch is opened or a wire is cut, you have an open circuit. When the circuit is open, no current flows. So that's the idea again of plugging in the outlet, taking your plug and plugging in the outlet. Before you plug it in, it's open, there's no current flow. Once you plug it in, closed circuit, now it's ready to flow. Open where it can't flow, closed, can flow. Parallel circuits. So now if you look at this picture here versus the other one line, one path. This one now can actually go in two different places. You can go to the first bulb or the second bulb. If you cut the second bulb, you can still have the first bulb because there's still a path for electrons to flow. Remember, it wants to go all the way from that positive terminal to the negative terminal every time, because electrons are going to go from the positive to the negative side. They want to move around to get to the other side. Parallel circuits provide multiple paths, so more than one path, 2, 3, 4, 5, 50,000, whatever it is. The total current through the circuit equals the sum of the currents through all of the devices. Okay, same thing here. Because there are multiple paths for current, the overall resistance of the circuit is decreased. You calculate the total resistance using reciprocals. What is a reciprocal? It's 1 over a number. So in this case, it's 1 over the resistance of each of the resistors. So R1 would be our first light bulb in path 1, and R2 would be our second light bulb in path 2. So those each have a resistance amount, and you'd put 1 over that, and you'd get your total resistance. A little bit different, just another equation to look at. So we're still looking at I is equal to change in voltage over resistance. Or yes, current is equal to change in voltage over resistance. So remember, each resistor is the ratio of the voltage drop across the device and the resistance of the resistor. Voltage drop across the device is the same and equals the potential difference of the power supply. Same sense as number, so same here as there for the voltage drop. All of it looks the same. Okay, here's a resistance. These are our resistors. We looked at these in class a little bit before too. Helped me organize them. Resistors are made of long wires, carbon or semiconductors. The value of the resistance is labeled on the outside of the resistor. Sometimes it's color-coded bands. I'm going to give you another informational sheet on the actual reading of those color bands. Make it a little easier. I didn't want to put it in this video because you'd have to reference this again and give it to you separately. But you can tell different types of resistors by looking at just the colors. There's a pretty accepted standard in that as well. All right, 4 more questions. Good luck. Take a pause. Answer the questions. Okay, here's the answers. Series. So which type of circuit has constant current throughout? Series. Which type of circuit has constant voltage? Parallel. What is the formula to calculate total resistance in a series circuit? VIR, right? Oh, no, not right. Resistance, we gotta read our question. Total resistance in series circuit. R total, R1 plus R2. What is the formula to calculate total resistance in a parallel circuit? So total resistance in a parallel circuit using reciprocals. 1 over the resistance total is equal to 1 over R1 plus R2. So reciprocals is parallel. No reciprocals is series. All right. Take the quiz. Good luck.